So inequalities and the modulus function. So inequalities and the modulus function. So let's consider a number line. So let's consider this number line here. This is where we have our 0. And if we move one space to the right, so let's say this is 1, we could say that we've successfully covered a distance of 1. Similarly, if we move one space to the left, we could say that we covered a distance of 1. So even though we are moving in a negative manner, we've still covered one space. Regardless of it being positive or negative, it's just one space. So the distance moved would be an absolute value, which is still 1, and we represent this using this symbol. So this symbol means the modulus or absolute. And if we take the modulus of 1, this is going to result in 1. If we take the modulus of negative 1, this is going to result in positive 1. So if we take the modulus of a number, the result will always output the positive value. Because even though we're moving to the left here, we know that in reality this is a negative movement, because we're on the number line, we're moving to the left. So that's where we end up at negative 1. However, modulus, it doesn't consider the direction per se. We're only considering the distance moved. So we only move one space. Regardless of to the left or to the right, it's just one space that has been moved. Hence, if we take the modulus of a negative, the result will be a positive of that. Now, as it relates to variables, if we take the modulus of x, this will result in x. Modulus of x is simply the negative of negative x. That is when x is a negative number. So if we have a negative x value here, and we take the modulus of it, we just get the positive value. That's what it's saying. Modulus of 0 is equal to 0 when x is equal to 0. This is when x is equal to 0. The modulus of 0 would just be 0. Now, what is the purpose of these things? We can actually use them to solve equations involving modulus. So let's add a page. So solving equations involving modulus. So if we have the modulus of x plus 1 being equal to 5, and we need to solve for the possible values of x. Now this is going to give us two values of x. So from this we're going to get two solutions. One where we take the positive x. So this is where x plus 1 is equal to 5, and we know that x is equal to 4. The other solution would be if we say negative x why did I have that there? So it's negative x still plus 1. Yeah, so negative x minus 1. So what happened is that we took the negatives of both of these in the bracket or in the modulus sign. So negative x minus 1 is equal to 5. So negative x is equal to 6. X is equal to negative 6. So that's one way we could look at this. Another way, which is the way that is commonly recommended, is that we square both sides. This is the way that is recommended to avoid any mistakes, to know what to change to negative, what to change to positive, and so on. So if we have the modulus x plus 1 being equal to 5, what can happen is that we can square both sides. So if we square both sides, and we're going to ignore the modulus symbol for a second, we'll have x plus 1 all squared is equal to 5 squared. So expanding this, we'll get x squared plus 2x plus 1 is equal to 25. And then we just transpose, get our quadratic, and solve. So x squared plus 2x minus 24 is equal to 0. AC method now, this is 6 and 4. So x squared plus 6x minus 4x minus 24 is equal to 0. Then we say x plus 6 minus 4 x plus 6. So x minus 4 and x plus 6 would be our two factors. So therefore x is equal to 4 and x is equal to negative 6, which is what we have up here. So whichever way, I know this way up here is shorter. However, if you're comfortable squaring both sides, then that's fine. Do what makes you comfortable. You will still end up with the same answer. And remember, I said that if we square both sides, we have a better chance of not making any mistake, because sometimes you might get multiple terms here where you have to take the negatives of them. So it all depends on what you are comfortable with. So look at this one. We have the modulus of 2x plus 3, and this is equal to 12. We need to find the possible solutions of x. That's going to give us our answer here. So what we can do now is either we're going to square both sides, or either we're going to take the negatives of the left hand side. So which one do you want us to do?
Square both sides. Square both sides.
Alright, so let's square both sides. So on the left hand side here, we have 2x plus 3 all squared should be equal to 12 squared. So expanding this, we get 4x squared plus 12x plus 9 is equal to 144. So 4x squared plus 12x minus, so we're going to transpose that, so that's what 135 is equal to 0. Now using up AC for this one, 4 times 135, that's 270, 540. That's a big number. So 540. We need two numbers when we, so we're dealing with 540 as the AC. We need two numbers. When we add them, we get 12. And looking at this, seeing that it ends with a 0, this tells me that either we're going to be dealing with a 4 and a 5, 4 and a 5, 5 and a 8. So it's either 5 or a number that ends with 0. So for example, 10 times something, 20 times something, 30 times something. So one of those combinations we're dealing with. Either a number that ends with 5 or a number that ends with 0. That's the only way we can get a 0 here as the last digit. So let's look at the possibilities for zeros. If we're looking at 10, it will be 54 times 10. That's not going to give us 12. If we're looking at 20, it's going to be 27 times 20. That's not going to give us 12. If we're looking at 30, it's going to be, that's what, 18 times 30. All right. So 30 times 18, and this we can get a 12 from it. So that means we are looking at 4x squared plus 30x minus 18x minus 135 is equal to 0. Factor out 2x, we're left with 2x plus 15. We factor out 9, negative 9. We're left with 2x plus 15, that's 0. So 2x minus 9 and 2x plus 15. So therefore x is equal to 9 over 2 and x is equal to negative 15 over 2. And those would be your two solutions. Are we clear?
Yes, sir. Yes, sir.
Then of course, we're going to look at if we didn't square it, what would happen. So remember, if we aren't squaring both sides, what we can do is just drop the modulus sign and say 2x plus 3 is equal to 12. Transpose to say 2x is equal to 9, x is equal to 9 over 2. So that's one of the solutions. So now the second solution is if we took the negatives of both of these. So negative 2x minus 3 is equal to 12. Negative 2x is equal to 15. X is equal to negative 15 over 2. So looking at this, I know you're going to say, boy, that the method here easy. So it's for you to decide which one you want to use. Okay? Let's see. If we have 3x plus 1 is equal to 13. Let's not use such a big number. Let's say 7. Alright, I want you to go ahead and find the possible x values for this. So find the possible x values. You have 3 minutes. Finish. Alright, so I'm seeing here in the chat x is equal to 2 and x is equal to negative 8 over 3. Can anyone else confirm?
Sir, I did send the answer in the WhatsApp group, but yeah.
Yeah, I'm reading from the WhatsApp, the one that you sent. So I'm asking if anyone else got, if Alexis got that answer as well. Lamik?
So I can't find the factor. I'm having trouble finding a factor that I'm going to.
Oh, you squared both sides.
Yes, sir.
So squaring both sides, 3x plus 1 all squared is equal to 7 squared. So 9x squared plus 6x plus 1, 49. So this is 9x squared plus 6x minus 48 is equal to 0. So now 9 times 48, that's 360, 432.
No, sir. 32, negative 432, sir.
432. Alright, so we're looking for factors that will give us 6 when added. Alright, so that's the positive number will have to be bigger than the negative number, seeing that we have a positive 6 here. Alright, so to get 2, we're looking for 4 and 3. That's to get 2 at the end here. We're looking for 6 and 2. We're looking for 2 and 1. Or we're looking at 9 and 8. There are many combinations to get 2 at the end, 7 and 6. But I think that will cover all of them. Alright, so 2 factors now that will give us 432. So I want to get 6. Oh, and 4 and 8. So 4 and 8 would open up the possibility of 24 and 18. I think 240. I think this might be the one that we're looking for. Let me double check. 24 times 18.
Yes, sir, that's the one.
Okay.
So it's positive 18 and negative 20. No. Positive 24 and negative 18, right?
Mm-hmm.
Okay.
Is equal to 0. So we can factor out 3x. So that's 3x plus 8. Factor out minus 6. So that leaves 3x plus 8. So 3x minus 6 and 3x plus 8. So that means x is equal to 2 and x is equal to -8/3. So those would be the two solutions of x that satisfies this modulus inequality. Good?
Yes, sir.
So a tip when you're doing AC method, when you get a large number like this, you'd have to look at the last digit and see what are the last digits of your multiplication. So 4 and 3 can give us something with 2, 6 and 2, 2 and 1, 9 and 8, and so on. So once you identify all the possible last digits, you can go ahead and play around with them. So this could have been 24 and 23, but this looks like it's going to be bigger than that. 26 and 22 looks like it's going to be bigger than that. 22 and 21 this is bigger than that as well. So you'd have to just play around with these possible combinations to see which one would fit and which one is going to give you a difference of 6. That's the other thing as well. Alright, so that's it for that one. And of course, you know, you could get modulus inequalities when both sides of the equation is going to involve a modulus. So over on the left hand side, we have 2x plus 1, and we're told that this is equal to the modulus of 3x minus 4. So what we'll have to do is square both sides. So square both sides. So in squaring both sides, we end up with 4x squared plus 4x plus 1 is equal to 9x squared minus 24x plus 16. We'll just transpose to get everything on one side. So I'm going to be transposing over on that side. See that the 9 is bigger than the 4, I'm going to bring that over. So we'll be left with 5x squared minus 28x plus 15, and that's equal to 0. So our AC here is 75, and we need two numbers. That's going to give us 28. So that's 25 and 3. So we can say 5x squared minus 25x minus 3x plus 15 is equal to 0. So factor out 5x, we're left with x minus 5. Factor out -3, x minus 5. So 5x minus 3 and x minus 5. So therefore x is equal to 3/5 and x is equal to 5. It's not and, it's or. So both of those could be your solutions to this question. So if we get it where the modulus is on both sides, all we'd have to do is square both sides and we'd get our solution. Now, of course, the modulus symbol doesn't have to be around the entire equation. Let's look at this one. Find all the values, get back to it. So it was x squared minus 6 x plus 8 is equal to 0. So remember, we said that one of the solutions would be when we just take the x value as is. So we would have x squared minus 6x plus 8 is equal to 0. And then using AC method, this is going to be x squared minus 2x minus 4x plus 8 is equal to 0. So we factor out x. Factor out negative 4. So x minus 4 and x minus 2 equals 0. So x is equal to 4 or x is equal to 2. This is one of the solution sets. The other one would be if we took the negative of this x here. So what I mean by that is if we had x squared minus 6 and then we take the negative of this, plus 8 is equal to 0. So this would be x squared plus 6x plus 8 is equal to 0. Following? Following?
Yes, sir.
So we just took the negative of what was in the modulus symbol. Alright, so over on this side now, using AC method, we have x squared plus 4x plus 2x plus 8 is equal to 0. So we factor out x, and we're left with x plus 4. We factor out 2, we're left with x plus 4. So we have x plus 2 and x plus 4 being equal to 0. So x is equal to negative 2 or x is equal to negative 4. So those would be our solutions to that question there. So let's look at another way which these questions can be formulated. So for example, we're given this to solve. The modulus of 2x plus 1 times x minus 2, and that's equal to 0. This can be represented as the modulus of individual factors. So we're taking the modulus of two things being multiplied. We can treat this as the modulus of individual factors to say that this is the same thing as the modulus of 2x plus 1 Welcome, you're very early. So what I was saying is that we can treat this as the modulus of 2x plus 1 times the modulus of x minus 2, and this is equal to 0. So now, dropping the modulus symbol, we will get 2x plus 1 times x minus 2 is equal to 0. So this is just two factors where 2x plus 1 is equal to 0, and x would be equal to negative a half, or x minus 2 is equal to 0, where x is equal to positive 2. So this is just how we would work out a question given to us like this. We could just drop the modulus symbol and evaluate as how we would for a quadratic equation. Now, we can also be given these types of questions as well in the form of fractions. So let's look at how we would do that. So if we're given these in the form of fractions, where we need to solve the modulus of 3x plus 1 over x plus 2, and we're told that this is equal to 2. So what is usually recommended is that we square, well, not square, we multiply by the square of the denominator. So whenever we're dropping the modulus symbol, we can multiply by the square of the denominator, or we can do this the old-fashioned way to say that the modulus in this form is the same thing as the modulus of 3x plus 1 over the modulus of x plus 2, and that's equal to 2. So that's how we can treat it. Then we can say that we can drop the modulus and keep our brackets. But remember, whenever we drop the modulus, we'll have to find the we'll have to use the negative of that as well. So what that is saying to us is 3x plus 1 divided by x plus 2 is going to be equal to 2, and then we're going to be transposing this over here. So 3x plus 1 is going to be equal to 2 times x plus 2. This will give us one of the solutions. So 3x plus 1 is equal to 2x plus 4 transpose. So 3x minus 2x, so x is equal to 3. That's one of our solutions. The other solution now will come from us taking the negative of one of these modulus. So if we took the negative of the numerator, we'll still get the same answer. If we take the negative of the denominator, we'll still get the same answer. So we can take the negative of either one, but seeing that we're going to be transposing the x plus 2, we're going to be taking the negative of that to get the other solution. So the second solution will be, so if we have 3x plus 1, we're going to be taking the negative of the modulus that was down here. The x plus 2 will be taking the negative of it. So it's the negative x minus 2. And this is going to be equal to 2. So similarly, we transpose and we get 3x plus 1 is equal to 2 times negative x minus 2. So 3x plus 1 is equal to negative 2x minus 4. We transpose 5x is equal to negative 5, x is equal to negative 1. And that would be our second solution. Any questions on that?
Sir, can you go over that one more time, please?
Alright, I'm going to go over it, but I'm going to try squaring it. Alright, so what we had was the modulus of 3x plus 1 over x plus 2 being equal to 2. So I'm going to be squaring both sides. So let's square both sides and see if we end up with the same answer. So when we square the left hand side, we end up with 9x squared plus 6x plus 1 over x squared plus 4x plus 4, and that is equal to 4 because we're squaring both sides. So now we're going to transpose this 4 over, well, not the 4, we're going to transpose this over here. So we're going to have 9x squared plus 6x plus 1 is equal to 4x squared plus 16x plus 16. Alright, so now we'll do some transposing. 5x squared minus 10x minus 15 is equal to 0. And from this, I notice we can divide throughout by 5. So x squared minus 2x minus 3 is equal to 0. Applying AC method to this, we have x squared minus 3x plus x minus 3 is equal to 0. So we factor out x minus 3, we factor out 1, x minus 3. So we have x plus 1 and x minus 3 is equal to 0. So x is equal to negative 1 or x is equal to positive 3, which is what we have here. So I think if we square both sides, we should have a better chance of getting the solution than if we try to be fancy and say, alright, I'm going to be taking negative of this, then I'm going to be taking positive of this one, or negative of this one and positive of this one. So let's just square both sides and get our solutions, okay? Are we clear?
Yes, sir.
So we can just square both sides and we're good. That will give us our solutions that we need. However, for the one that I was doing, that one, squaring both sides proved challenging for that one. It's going to take some time to straighten it out because we're going to get to the fourth power, and then you know that's going to be 4 different solutions there. Alright, so let's look at when modulus meets inequalities. So modulus inequalities. So given any constant c, the mod of x is less if and only if x ranges between c and positive c. So let's look at this. This saying to us that given any constant c, the modulus of x is less than this constant. So the modulus of x is less than this constant if and only if the value of x ranges between negative of that constant and positive of that constant. So what this is saying to us is, if we're told that x is equal to 3, for example, and the constant we're dealing with is 5, we know that the modulus of negative 3 is going to be positive 3. We know that the modulus of 3 is going to be 3. So the modulus of that 3 is going to be less than positive 5 or greater than negative 5. So that's what they mean by that. So we want to look at an example of this. So if we have the modulus of x plus 2 and we're told that this is less than 5, what we can do in this case is write it in the form. So we need to write it in the form where x is less than the constant greater than negative of the constant, and the constant in this case is 5. So we need to write it in the form where x is greater than the negative of this constant but less than the positive of this constant. So what I mean by that is we're going to take negative 5 and we're going to say that negative 5 is less than the modulus of x plus 2, and this is less than 5. So the idea behind this is that we want to get a range of x values that would satisfy this inequation. So we can drop the modulus sign now to say negative 5 would be less than x plus 2. X plus 2 is less than positive 5. So to solve for x, we need to get rid of this positive 2. And the only way to get rid of positive 2 here would be to subtract. And if we subtract positive 2 from the x, we'd have to subtract it from both sides. So subtract 2, subtract 2, and we subtract 2 from the middle. So I'm going to rewrite that in another line. So we'll have negative 5 subtract 2, then we'll have x plus 2 subtract 2, and 5 subtract 2. So it's basically like the balance method of equations, where whatever we do to one side we do to the next. So we're going to be subtracting 2 from everything just because we need to get rid of this positive 2. So this is going to be negative 7 and 3. So this would be the solution to this question. So all we need to do is to put the modulus in between the inequalities, transpose, and get our solutions. Alright, so let's look at one more example. Find the set so we have modulus of 2x minus 1 is less than 7. So the x is less than the constant, so we can go ahead and write it in our form where we have negative 7 is less than 2x minus 1, and this is positive 7. So we simply transpose. So to get rid of this negative 1, we'd have to add 1 over here, add 1 over here. So this is simply negative 7 plus 1, 2x, and then 7 plus 1. So this is negative 6, and this is 8. And to get rid of this 2, we simply divide by 2 on all three sides. So this is negative 6 divided by 2, and that's x. 8 divided by 2, so this is negative 3, and this is 4. So this would be your solution to this question. All we're doing is transposing per se, but we're doing it on two sides of the inequality. Clear?
Yes, sir.
Yes, sir.
So here's another scenario that we may encounter, and this one says given a constant, so this is like another rule. So given a constant c, the mod of, so this is in the greater than scenario, the mod of x greater than c would fall between, so the mod of x greater than the constant if and only if x is greater than the constant and x is less than the negative of the constant. So this is very similar to what we just did. However, what it is saying to us is if the modulus of the x value is greater than the constant, we're going to have two different range of values. That's the only thing that it's saying differently. While if it is less than the constant, we're going to have one specific range of values. Now let's look at an example for this one. The modulus of 3x plus 1 is greater than 7. So this is in the form where the mod of x is greater than a constant. So once it is in that form, we know we're going to have two different solution sets. One where we're looking at x being greater than the constant, and for this one we simply say 3x plus 1 is greater than 7, and we'll just transpose and get x by itself. So 3x is greater than 6, x is greater than 2. So this would be one of your solution sets. The other one would be where x is less than negative of the constant. So remember, this is representing x. So we have 3x plus 1 is less than negative 7. So we bring this over, we get 3x is less than negative 8. X is less than negative 8 over 3. Now is that clear? One condition is when, so if we have a modulus of something is greater than a constant, we know we are going to have two different solution sets. If the modulus is less than the constant, we're going to have a joint solution set. Now, something to note, the modulus of x is less than the modulus of y if and only if x squared is less than y squared. So if x squared is less than y squared, then the modulus of x must be less than the modulus of y. That's just one of the inequality theorems as it relates to modulus. And from this we say solve the inequality mod of 2x plus 5 is less than the mod of 2x minus 1. So what this means is that, or what this is allowing us to do is open up the possibility of squaring both sides. Because they told us that the mod of x is less than the mod of y. This would be the mod of x, this would be the mod of y. And if the mod of x is less than the mod of y, then we can just square the x, square the y, and simplify. So let's square both sides. So mod of 2x plus 5, we're going to square this. We have 2x minus 1. We're going to square this as well. So squaring this side will give us 4x plus 20x plus 25 is going to be less than 4x squared minus 4x plus 1. So 4x will cancel 4x. So that cancels that. So we have 20x plus 4x is less than 1 minus 25. So 24x is less than negative 24. X is less than negative 1. Alright, so something to note. The inequality sign changes under two conditions. We have division and multiplication. and this would be by a negative. This is something you should have known from before anyways. Alright, so we've looked at most of the crucial stuff so far. We want to look at some theorems of inequalities before we get into some, I think graphs is what comes next. Alright, so theorems of inequalities. So if A is greater than B, then A plus C must be greater than B plus C. That one is self-explanatory. If A is greater than B, and if we're adding A to a number, it must be greater than if we're adding B to that same number. So that's one of them. The next one, if A is greater than B and C is greater than 0, then AC must be greater than BC. Self-explanatory once more. If A is greater than B and C is less than 0, then AC is less than BC. And lastly, if A is greater than B, then 1 over A is less than 1 over B. These are theorems that doesn't take much for us to figure them out. And well, I can leave this question until we get to our past paper revision. That one is a past paper question. Let's see. So I think we can do some solving inequalities now in terms of identifying the range. Solve the inequality. So here we have modulus negative 5x plus 3 is less than or equal to 12. And they say to us, solve the inequality. So looking at this, we must first assess what they want from us from this question. If we're solving this inequality, we know that, or based on what we just discussed, we know that if x is less than the constant, we're going to have a joint solution set, right?
Yes, sir.
So what we can do now is just put our negative 12 over here and put our negative 5x plus 3 in here and put our positive 12 over here. This is going to give us the joint solution set. So now we just transpose. Subtract 3 over here, subtract 3. So that's negative 15 minus 5x. And this is going to give us 9. Alright, so here is what we have now. In order for us to get x by itself, we'll have to divide by negative 5. And what we say happen when we divide by negative 5? Well, what we say happen when we divide by negative, sorry.
The sign, the inequality will change.
Exactly, the inequality is going to flip. So you see how this one is set like that? It's going to turn the other way. And this one is going to turn the other way as well. So what we will have is that... Alright, so I'm going to do it first before I flip the inequality. So we divide by negative 5 over here. We're going to get 3. And then the sign is going to flip. And we have x in the middle. This sign is going to flip. And we have negative 9 over 5. Clear? Because we're dividing by negative 5 there. Negative 5 there. Are we clear? However, we can't write inequalities like this. X is less than 3, x is greater than... No, we can't write it like that. We have to start from the smallest possible x value, which would be negative 9/5. And then we say that x is greater than that value. And
I didn't understand.
X is less than or equal to 3. Hold on, give me a second here. Alright, sorry about that. Alright, so where were we? So yeah, this would be the solution to this question. We're almost finished with this topic. There is only 2 other quick things I want to show you guys. Let me look for them. So as I've stated, this isn't a very difficult topic. So the last thing we are looking at for this is quadratic inequalities, and this is where the graph will come in. And for the graph, we'll be shading specific regions of the graph. So quadratic inequalities.
Sir, if you're talking, your mic.
Yes, I was indeed talking. Alright, so I'm saying the last thing under this would be quadratic inequalities, and this is where the graph would come into play. We would have to shade specific regions of the graph. So quadratic inequalities. So remember that modulus, let me get that. Oh, that's not needed in your... Oh, I thought that would have been... Oh, but what I was referring to is if we had a graph looking like this, and a piece of the graph would end up down here. If we're doing the modulus of this graph, we'd have to put the graph above, but I'm not seeing it on your thing, so I'm assuming that it is not required of you. Alright, but we'll just look at the regions of the graph which we should shade. So we'll start with an easy example. So to solve a quadratic graph which is greater than 0, we must first graph the function. So if we have a quadratic in the form ax squared plus bx plus c is greater than 0, where a is not equal to 0, we must first solve the function, or graph the function rather, so this is what we must first graph, and then we would need to identify the specific values of this graph. So for example, the minimum point or the x and y intercept, if we are required to graph this, because sometimes they won't ask you to graph it, they will just ask you to represent this the range of values which would satisfy this inequality. For example, this one. So you could have it being greater than 0 or less than 0. So an example, find the range of values of x for which x squared minus 3x plus 2 is less than 0. So we need to find the range of values of x for which x squared minus 3x plus 2 is less than 0. So now, in order for us to find these values, we would need to find the roots of this quadratic. So we must first solve it. So x squared minus 3x plus 2 being equal to 0, applying AC method, x squared minus 2x minus x plus 2 equal to 0. Factor out x, is equal to 0. So we have x minus 1, x minus 2, x is equal to 1, x is equal to 2. So those would be the solutions. And we know, or I'm assuming that you guys know, that the x values are the roots, and those would be the points where the graph cuts the x-axis. So it would cut at 1 and it would cut at 2. We know that, right? And the value here, the c value, is our y-intercept. So the only other thing we would need from this is to find the minimum value of the graph. And remember how to find the minimum value. We can find that minimum value by saying x is equal to negative b over 2a. So the minimum would be at h, comma k. Minimum or maximum would be at hk, where h is equal to negative b over 2a and k is equal to 4ac minus b squared over 4a. So these are the formulas from completing the square, where we will use to help us find the minimum point of this graph. So h is equal to b over 2a. So this is b, and the a would be 1. Well, negative b. So the h value is at 3 over 2. And the y value is at negative 1 over 4. So let's say somewhere here would be our turning point of this graph. So if we are to sketch this now, it's going to look something like this. It's going to come down, go through here. I'm not drawn to scale. Let me do the curve part first. So right here and right here. Right, so let's say our graph is looking something like that. And remember that they said that they want us to show them where this graph is less than 0, right? So where the graph is less than 0 is going to be below the x-axis. So this is the region of values that would satisfy our graph being less than 0. However, they want these as an inset builder notation. So we'll have to write it as x would be greater than 1 and less than 2. So x where this is 1 and this is 2. So these would be the set of values that satisfies this graph. So any value that we select between here, the x is going to range from 1 to 2, right?
So go again, please.
I'm saying this shaded region down here, if we select any x value, it has to be between 1 and 2. Any x value we select in that region. So that would be the region of the graph where x squared minus 3x plus 2 is less than 0 because it's below the x-axis. And remember, that if this is our function here, write it on another page. So that's x squared minus 3x plus 2. So that's x squared minus 3x plus 2 is less than 0. Another way we can express this is the same thing as f of x, right? So we can say f of x is equal to x x squared minus 3x plus 2. Right? We're on the same page. We can see that.
Yes, sir.
So now another way we can represent f of x is y. So y is equal to x squared minus 3x plus 2. So what this is saying to us is that we're looking for the region where y is less than 0. So looking back at the graph, this is the y-axis and this is the 0, the point where y is equal to 0. So all values below here would have a value, so -1, -2, -3, and so on. So all y values below the graph, below the x-axis, will be equal to, or will be less than 0. So we're looking for the piece of the graph that falls in that category. So this piece of the graph that is shaded is where the y values are less than 0. Cool?
Repeat that last thing again one more time, sir.
So I'm saying that below the x-axis here, all y values going down this way are negative. And what the question asks for us is to find the range of x values for which y is less than 0. So when we construct the graph, we're looking for the piece of the graph where all of the x values we substitute in this function is going to give us a negative y value, a value that is less than 0. So all the values down here would satisfy that condition. So if we take any x value below here and substitute in this, we're going to get a negative y value. So a value that a point that would appear here would be 1.5, right? 1.5 would be in this range. You can see that.
Yes.
So let's test 1.5 in this to see if it's going to give us a negative y value. So 1.5, so when x is equal to 1.5, which is the same thing as 3 over 2. So when x is equal to 3 over 2, we're going to substitute here. Y is equal to 3 over 2 all squared minus 3 times 3 over 2 plus 2. So this is 9 over 4 minus 9 over 2 plus 2. So that's 9 over 4 minus 18 over 4 minus 8 over 4. So that's negative 17 over 4. So this is a negative y value. So any x value we select in this region, we're going to get a negative y value for that. That's what this is saying to us. So let's look at one where we're looking for a positive region. And then we look at the sign table, and that will be the last thing for today. Let's look at a positive example. Solve the inequality negative x squared plus 4x minus 3 is greater than 0. So whenever we get a question like this, we must first assess what type of graph we're dealing with. So this the a coefficient of the x squared is negative. That should automatically tell you that the graph we're dealing with is a frown. Right? So we're going to get a frown when we do this graph. So now we would need the values that are going to satisfy this graph. So we could say let f of x, let's use y. So let y be equal to negative x squared plus 4x minus 3. And then when y is equal to 0, that's going to give us the roots. So negative x squared plus 4x, because we want the roots of this quadratic. So using AC method, what's this? That's positive 4. So that's 2 and 2. Minus 3 is equal to 0. So if we factor x, we get negative x plus 2. And if we factor... Wait, that's not going to work. Oh, wrong AC. Why did I put 4 there? It's positive 3. So it's minus x squared plus 3x plus x minus 3. So we factor out x. We're left with negative x plus 3. We factor out negative x. We're left with negative x plus 3. So x minus 1 negative x plus 3 is equal to 0. So x is equal to 1 or x is equal to 3. So those will be the two solutions that will be on our x-axis. So now the only other thing we would need is the turning point. And seeing that this is a frowning graph, we're going to have a maximum point. So we can find h by saying negative b over 2a, and that's going to be negative b over 2a, so that's positive 2. So h is equal to negative b over 2a, so this is positive 2. And then our k value would simply be, we can substitute the 2 in the equation to get what k is. So that's negative 4, positive 4 minus 3. So k is equal to 1. So we have our hk value, we have our x values. Now it's time to construct the graph, because they might ask you to sketch the graph and shade the region. So it would be good to know how to go about assessing these graphs. Alright, so based on all the information we have, the turning point, or the y-intercept, sorry, is at negative 3. The x value is at 1 and 3. This is at 2 and 1, so roughly here. This is hk, 2 comma 1. So now we need to construct our curve, and it would look something like this. Remember, it doesn't have to be as accurate as ever. All you need to do is to ensure that you have all the critical points. So this is at 1 and 3, such and such. So now the region we're looking for is where the graph is greater than 0. So where it is greater than 0, that's our focus, and it's going to be this little region here. So all x values in this region is going to give us a positive y value if we substitute here. Are we clear? Any confusion with this one?
No, sir.
And then we didn't answer the question as yet, because if they say solve the inequality, what they want from us is to give them the solution set. So they want the range of x values. So what are the values, or what is the range of x values that would satisfy this inequality based on everything you're seeing here?
You want like the range, so it would be 1 is less than x, but x is less than 3.
So that would be our range of values, and this would be the solution. Alright, very good. So now the last way they can give us any form of inequality question on these papers is as a fraction, and this is where something known as the sign table will come in. Some people use number line to do it. I would rather to sketch it and shade the region, but you don't know what they might ask. So the sign table. So the critical values of a function are the values of x Alright, so the critical values are basically our solutions to the function. And if the function is given in the form where we have two functions of x being divided in each other, then we can simply solve the numerator, solve the denominator, and those values would be the zeros of the function. Of course, we'll be looking at some examples and how we can apply the sign table to these questions. Alright, so find the critical value or what the question will say is find the set of values of f of x is equal to 2x plus 1 over x minus 1. So if we're looking for the critical, find the critical values. So if we need to find the critical values of those, we're basically looking for the zeros of the function. And we can do so by saying numerator is equal to 0, denominator is equal to 0. So 2x plus 1 is equal to 0, 2x is equal to negative 1, x is equal to negative a half. Or x minus 1 is equal to 0, x is equal to 1. So those would be the zeros of the function. If we substitute any one of those in the function, it's going to result in 0. Alright, so we can use the critical values to solve inequalities by drawing up the sign table. Now, a sign table consists of the factors of the function and non-overlapping intervals. So that's what makes up the sign table. So you'll see what I mean by that. So I don't think I want to start it on this page. Let me just start it fresh. So if we're looking for the set of values of x satisfying the inequality x squared minus 5x plus 4 is less than 0, and we want to use the sign table. So the first thing we need to do is to find our critical values. So the critical values of this will require us to use AC method to solve this. So that's x squared minus 5x plus 4 being equal to 0. Then we say x squared minus 4x minus x plus 4 is equal to 0. From that, we get x minus 4 x minus 1 x minus 4, where x is equal to 1, x is equal to 4. So those would be the critical values. So the critical values are x equal 1 and x equal negative 4. So you have to do it in ascending order. And if we were to identify the critical values on the number line, we would be looking at a region where nothing is overlapping. So this is our number line, and we have 1 and 4. So this would fall within a region like that. So between 1 and 4 would be the region of interest. So right here would be where we're interested in, between 1 and 4. So now a sign table can actually help us to identify our solution set. So how to do a sign table? On the, so let me use my, so let's say this is our sign table here. Nothing will go here. Alright, so the first thing we need to put in our sign table is our factors. So based on the quadratic we have here, the first factor, x minus 4. That's one of the factors, right? Another factor, x minus 1. And if we combine both of these factors, it's going to be x minus 4 times x minus 1. Are we clear?
Yes, sir.
And then you know that when we combine the factor, it will give us back the original quadratic if we expand. So that's what we write in the row up here. So now going down on the side over here, we're going to be putting the possible solution sets. So firstly, we could have a set of solutions that are less than 1, right? If we didn't know the number line or anything like that, we could have a set of solutions that would be less than 1. So we're going to say where x, let me use a different color, where x is less than 1. That's the region we're looking at, where x is less than 1. Another region we could look at is when x is between 1 and 4. So when x is between 1 and 4, that's a region of interest. The other region is where x is greater than 4. And those would be our 3 possible solution sets. So now let's look how we use these solutions to help us. So firstly, if we're interested in the region where x is less than 1, what is that saying to us? It's saying that we can use values such as 0, -1, -2, -3. Any value that is less than 1, right, would fall in this region. So what we're going to do is pick a random value that is less than 1. One such value would be 0. So if x is equal to 0 and we substitute it here, what will we get?
Yes, sir. Repeat the question.
If x is 0 and we substitute it here, what will we get?
-4.
So we will get a negative. So this means negative. We'll get a negative
Oh, okay.
answer. And if we use -2, we still get a negative. If we use -20, we still get a negative. So same thing here. If we use those negative values, what do we get?
Negative.
Still negative. And over here, what's happening is that we're multiplying the two factors. So negative times negative would give us
Positive.
positive. So if this factor is a negative with the x values, this one is a negative with the x values, we're going to get a positive solution set. So similarly, we want to pick values between that is greater than 1 but less than 4. So one such value could be 3. Let's say we use 3 here for the x. When we use 3, it's going to be 3 minus 4. That's going to give us negative. When we use 3 minus 1, that's going to give us positive. Positive times negative, negative. Lastly, if we select any value greater than 4, so let's say 5. If we put 5 here, that's going to give us a positive. If we put 5 here, that's going to give us a positive. Positive times positive, positive. So now let's answer the question. So the question is asking us, find the set of solutions of x where this is less than 0. And if it is less than 0, we're looking for what?
The negative.
We're looking for negative. So the solution set that ended up giving us a negative result would be this one. So this would be your answer. And you'd say that the solution set is, so therefore the solution x where we have 1 less than x less than 4, and that would be your answer to this question. Now let's look at another one, and then we'll look at one where it involves a fraction, and then that would be it for today. Alright, so find the solution set, or you want one to try?
No, sir, you can do it. You can do it, sir.
Alright, solve the inequality. Alright, so once they say solve the inequality, what they're asking us for is the solution set. So we can quickly deduce our factors and our critical values. So we're going to just apply AC method to that. So that's 24, so that's 8 and 3. So 12x squared minus 8x plus 3x minus 2 equals 0. So we say 4x, then we get 3x minus 2 plus 1, 3x minus 2. So we have 4x plus 1, 3x minus 2. So from this, x is equal to negative a quarter, or x is equal to 2/3. So those would be the critical values that we're going to use to highlight our inequality. So let's draw up our sign table. Alright, so the factors that we have are 4x plus 1 and 3x minus 2, and then we're going to have a combination of the factors. So nothing will go here. So on the left hand side here, we're interested in the possible solution sets. So we look at the smallest of those x values and say if x were to be smaller than that value, then we look at the possible range that we could get from the smallest to the next one and say if x was to fall between -1/4 and 2/3, and then we say if x was to be bigger than 2/3. So you see how we get the possible solution sets?
Yes, sir.
So once you get the critical values, you just look at the smallest one and say what if x was smaller than that one, and then you say what if x fell between both of these, and then what if x was bigger than the big one, and that's it. So now our task is to select possible x values that will be smaller than this. So a possible x value that will be smaller than this is -5. So if we substitute -5 here, we're going to get a negative. But it would be best to try and substitute, well, even though if we substituted this exact value in this, we're going to get 0. So that means any value we substitute less than this, we're going to get a negative. And let's see what happens here. If we select a value that is less than this, so a value that could be less than this is negative. That's -1/4, negative. Yeah, it's still going to give us negative, because we have a -2 here, and if we selected -1, for example, this is still going to be negative. Yeah, so this is negative. Then when we multiply both of these, we get positive, right? So now if we selected any value between -1/4 and positive 2/3, so for example we selected 0. If we select 0 here, this is going to be positive. 0 here, this is going to be negative. Negative times positive, negative. And then lastly, if we select a value bigger than 2/3, so for example we select 1, that's going to be positive. If we select 1, that's going to be positive. So this is positive. So now to answer the question, they're asking us for the region where this is greater than 0. And if we're looking at where it is greater than 0, that means we're looking for positives, right?
Yes, sir.
So this is positive, this is positive. So these would be our two solution sets. And seeing that they aren't combined like this, how we'll write them is that we will say x, where x is less than -1/4. So this would be one solution set. Union.
Sorry, what I have.
Oh, sorry, let me fix that. Negative a quarter. Union. Then we just put the other solution set. X, where x is greater than 2/3. And that's how we would get our solution set. And if we were to put this on a graph, I'm just going to do this on Desmos so we can see what it's going to look like. So we have 12x squared minus 5x minus 2. And we're looking at the region where it is greater than 0. We'll minimize this for a second and let's zoom out. Hold on, let's zoom in. First things first, let's put it as equal to 0. So why is this looking like that? This not look right. Let me just get a regular quadratic. This one is tweaking. So we have minus x squared plus 4x minus 3. Alright, so let's see this one. Alright, so this is what this one would have looked like. And then if we're looking at the region where this is greater than 0, let's try greater than or equal to 0. Still the same. I wanted to show you the graph highlighting the region. However, I guess I would have to put that in as a separate condition. I think I would have to put that as a separate condition where 1 is less than x less than 3. I guess we'll have to just view it like this, where we can see the overlap in the graph would be between, so all of this green region is where x is greater than 1 but less than 3. However, where the graph is marking, or where it is enclosed by the graph, is the region where it is greater than 0. It's not giving me the best representation of that, but that's what it would look like. Alright, so we want to look at one last example of this, and this time we'll be using a rational function. So rational function is just one where we have a function of x in the numerator and denominator position. So let's look at one here. So rational So this one is very much similar like to what we just did. Very, very similar. So two ways to solve this. And the idea is to get it to be equal to 0. So if we have x plus 1 over x plus 2 is greater than 3, we can't just solve this as is because it is not greater than 0 per se. Okay, notice the ones that we did before are greater than 0, less than 0. However, this is greater than 3. So what we must do to solve this is transpose. We can bring over the 3, so we bring it over. And we get x plus 1 divided by x plus 2 minus 3 is greater than 0. And then we just simplify this side. So it's going to be 4x, hold on, it's minus 3, so it's minus 3x. So it's minus 2x. So minus 2x minus 2. Wait, that would be 3 times 2 is 6. Minus 5 over x plus 2 is greater than 0. So you'd have to simplify this part. I use equivalent fractions to simplify it, but that is what it would work out to be. And then once we get it looking like this, the next thing would be to do what? Alexis, what do you think? What's the next thing? We get it like this. What do you think we're supposed to do next?
So you would carry up the x plus 2 to be on the other side of the sign? Or no?
We would need to find our critical values. And remember we said that if we're dealing with a rational function, we can just equate the numerator to 0, equate the denominator to 0, and just solve. So we could say negative 2x minus 5 is equal to 0. X is equal to negative 5 over 2. And then we say x plus 2 is equal to 0. X is equal to negative 2. So that's one way. The other way is that we could multiply both sides by the square of the denominator. So this is what we have. We have minus 2x minus 5 divided by x plus 2 is greater than 0. We can multiply both sides. So multiply by the square of the denominator. So that means we can say x plus 2 all squared minus 2x minus 5 over x plus 2 is greater than 0 times x plus 2 all squared. And we know what's going to happen on the right hand side. That's still going to be 0. And on the left hand side, the denominator will cancel out the square. Are we seeing that?
Yes, sir.
So now we will have x plus 2 minus 2x minus 5 is greater than 0. So these would be our two factors, and then we still would have to solve like down here. So I think this method is a bit unnecessary per se, because if we're able to simplify our fractions like what we did here, we should be fine. We don't need to multiply by the square on both sides if we can easily simplify our fraction here. But if you are going to have an issue simplifying the fraction, I would advise you to just, well, you still have to simplify the fraction, yes. Oh, but as long as you simplify the fraction, you can just equate numerator to 0, equate denominator to 0, and solve. So we don't need to take the long route of multiplying by the square on both sides. So now we have our critical values, we have our factors. The last thing left for us to do is to find the sign table. So the sign table, we simply draw up some things for our factors. So one factor would be x plus 2. The next factor would be minus 2x minus 5. And lastly, combining these, would write them in its fractional form. So it's minus 2x minus 5 over x plus 2. And here is blank. And the first possible solution set, so we look at the smallest x value and say, what if x was smaller than negative 5 over 2? And then what if x was between, wait, yeah, that one is smaller. Yeah, still smaller. You realize that we're working with a negative 2 here. And then we say, what if x was bigger than negative 2? So if we select any x value here, we're going to get a positive. If we substitute that value here, we're going to get a negative. You can go through and double check these when I send the document. So this is negative, negative, positive, because we're dividing here. So positive divided by, no, negative divided by positive, negative, negative divided by negative, positive, and so on. So this is negative, positive, and this results in negative. So the region we're looking at is where it is positive, and the one that gave us positive is this. So we can say, therefore, x, when x is greater than negative 5 over 2, but x is less than negative 2. And that would be our solutions. So you can check the textbook to see more examples and practice the graph. Practice how to sketch the graph using the turning point and the roots. So with that said, this is where we will conclude modulus inequality. I think we've covered everything. I think we've covered everything that pertains to modulus inequality. Alright, so that is where we will end this session. The next time we meet, we'll be looking at functions, and remind me to send the notes on vectors as well. Alright, so enjoy the rest of your afternoon.
Same to you, sir.
Yeah, I'll try and sort out the recording. Let me stop.